Okay. So today I want to do really just three things, and I think that will take us to the end of the lecture. I realize I forgot to do it at the last lecture, so let me just cover this. I need to define what we mean by an adjoint of an operator. Most of you are already familiar with this, but I want to make a specific point in this definition. We're then going to talk about the spectrum of an operator, which is really going to be the crux of this lecture. And there's going to be a lot of information coming about the spectrum and the results of the operator. And we're going to expand more and more. So this whole section is about operator spectra. And in particular, I want to take us to the point where we're able to write down the spectral theorem for finite dimensional operators, and then later on we'll see if we can generalize that to infinite dimensional operators. And then I want to take one long example that will teach us something about the generalization of finite dimensional things to infinite dimensional things, and then it's going to be the idea of what right shift operator, just kind of a trivial operator to think about, but there's a lot to be learned. Right. Okay. So for the most part, then I want to focus on some definitions today. Again, most of these definitions you may already be familiar with from the context of finite dimensional linear algebra, but I'm hoping the way we package them now will force to infinite dimensional operators. Okay. So again, if you want to build some intuition, just keep referring back in your head to what you learned in second land linear algebra. Well, I hope you learned it. So the first thing I was just tie up the loose end from the last lecture, which has to do with adjoints, right? So what you would call a mission conjugate of an operator or a matrix in the finite dimensional case, right? So there you learned already that the adjoint of matrices play quite an important role in linear algebra. They're similarly important in the theory of operators in Hilbert spaces. And so we should take some time to just work out for ourselves once and for all what it means to say that an operator has an adjoint. In the finite dimensional case, in linear algebra, you have learned, given a matrix A, is exactly why I was actually this point. But given a matrix A, that its summation adjoint was the transpose and complex conjugate of all the entries in the matrix. Yeah, that's how you would have been taught this. But actually, the definition of an adjoint is more general. And when we go to infinite dimensions and start thinking about operators more generally, like differential operators, integral operators, then we need to be a little bit more careful about some of these involved. So let me say that in general, then, the adjoint of some operator let's say T there's a set of linear operators and some in fact this is so T lives in the set of bounded operators on some vector space, which for our case is going to be the Hilbert space. So this operator T is a bounded operator on Hilbert space. It's fine with the adjoint. By saying that the inner product of for two vectors x and y living in the Hilbert space, that inner product between Tx of x and y is equal to the inner product between x and adjoint of T acting on y. Right, so this pretty defines for us what we mean by adjoint, if it exists. If the inner product exists. Right. And if it exists in the norm of T, in the norm of its adjoint, I'll say. I invite you to check that in your standard second year linear algebra definition of what dagger meant, that this is the same thing as transpose and complex conjugate to all the entries in the matrix. Okay, but this is a far more general definition, and we can apply it to any operator that lives in a set of P of H. Okay. So if we have a differential operator, for example, you can define what the adjoint of differential of a derivative is. Okay. And if you've done second year Barton value problems, I hope this might not be unfamiliar to you from that context. So there you have the inner product defined by the usual integral, and you have some derivative acting on the one function. And you want to take that derivative and throw it into the other function, which is exactly what you would say if you were integrating by parts. Right? So you define there the adjoint of a derivative operator through integration by parts. We'll come back to all of this as we go along and talk about derivative operators and data as well. But I'm hoping that you would have seen this in some context before. Okay, this is the adjoint. And there's one point that I need to make about it, which is that the definition of the adjoint relies on the existence of an inner product. Right? So this idea that the adjoint is the transpose of the matrix of the complex conjugate is only there because you've already defined the inner product in that space of the dot product between the two vectors. Right, so you had an actual inner product in the space between in R3, for example, and that space, that inner product was the dot product, right? And so you define implicitly, probably didn't tell you this, but you define that operation of transpose complex conjugate precisely because this was true when this inner product was a dot product of two vectors. Okay, so the point I want to make here is that because the notion of an adjoint depends on the existence of an inner product, the notion of an adjoint is also pinned to that inner product. In other words, I could have an operator that is sorry, I want to say what I was saying. Okay. The adjoint of the operator is this, and the second point that I want to make is T is called self-adjoint, or what we call permission. If only if T equals T dagger, right? So again, going back to the final dimensional case, if you took the matrix and you flipped it about its diagonals, you transposed it, and you complex conjugated it, and it came out to be that these two were the same, then we said that this was a permission matrix, right? So permission operator defined the same way. If these two things are if then this turns out to be x T acting on y, then you said that this was a self-adjoint operator or permission operator, right? But what should be clear is that, again, this relies heavily on the fact that, it's pinned to an inner product. Okay, so we will come back to all of these things, again, in detail, when we talk about, when we talk about differential and integral operators. So now I want to introduce the idea, it's really quite an important idea, we're spending quite a lot of time talking about it, of the spectra of linear operators. Again, this is something that you've already encountered before, we're just generalizing it. So the finite dimensional case, when you talk about spectra of matrices, you're talking about a set of eigenvalues. And it's not the case here that they're always the same thing. But in the finite dimensional case, for sure, the spectrum is another way of saying a set of all the eigenvalues of the matrix. Okay. So again, if we want to go to iteration for what it is we're doing, then go back and think about the finite dimensional case, and what we're going to be talking about is a set of eigenvalues. And my goal for the next couple of lectures is going to be to state, prove some corollaries to the spectral decomposition theorem, which tells us how a given Hilbert space splits up into subspaces corresponding to each of the eigenvalues of a particular operator, and the conditions that make put on these operators in order to write down. This is what's called the spectral decomposition of a Hilbert space. And the corresponding theorem is called the spectral theorem. So we're going to state the spectral theorem for finite dimensional, state the proof spectral theorem for finite dimensional cases and bounded operators. And then I will just state what happens in the infinite dimensional case, because doing that is a little bit beyond this course. But I first need some definitions. So let's start by defining the spectrum of an operator. So suppose that the operator T lives in a set of linear operators in the Hilbert space H. Then complex number lambda is called a regular point of T. If the corresponding operator T minus lambda times the identity inverse exists and is bounded. In other words, it's called finite norm. Then if I take the set of all the regular points of the operator T, I gather them together, that's called the resolvent set of T. And we denote this by rho of t. The complement of the resultant set in the set of complex numbers is the spectrum of t. Now, the spectrum of t by sigma of t. So we already know that if the operator t is bounded, then so is t minus lambda times the identity. But not only is this t minus lambda and the identity bounded, if t is bounded, then so is t minus lambda and the identity inverse. Which means that the resultant set is not empty. And that the spectrum of a bounded linear operator is a bounded set. What tells us that it also tells us that the modulus of this complex number lambda is less than or equal to normal t for every lambda in spectrum of t. And this I want you guys to prove as an exercise. Yeah,
Let's say rho t does not equal some phi.
it's not empty.
Oh,
Yeah, not five.
sorry.
So just to make this a self-contained discussion, let's talk a little bit about value bound. vectors and eigenvalues. Right, so from your first course in linear algebra, recall that in a finite dimensional vector space, the linear operator is invertible if and only if it's one-to-one or onto. Okay. Yeah. Wait a minute. It said here, and now I'm talking about the finite dimensional case here, right? Is that lambda lives in the spectrum of the operator t if and only if t minus lambda I is not invertible. Lambda resides in the spectrum of the operator t if and only if t minus lambda times the identity as an operator matrix is not invertible. And in finite dimensions, this means that the kernel of the operator t minus lambda I is also not empty. And what this means is that we can always find some vector let's say A in this finite dimensional vector space V. With t minus lambda times the identity acting on A equals 0. That's what it means that the kernel is not empty. This some vector that I can find such that this operator acting on a vector maps to 0 over V. Okay. But that is the same thing as saying that t acting on A is lambda times the vector A. Which by definition makes A an eigenvector of t with eigenvalue lambda. So this is an eigenvector. Eigenvalue. So in words, what we just said is that in a finite dimensional vector space, every eigenvalue of an operator lives in its spectrum, and vice versa. All the elements of the spectrum of that operator are eigenvalues of the operator. Make sense? That's in finite dimensions, and it comes from the fact that in finite dimensions, this is not invertible, so it kind of like. Okay, so again, this is a statement from second year linear algebra. Okay, so you guys have definitely shown this when you're calculating inverses of matrices. I'm going to leave that for you to go and look. So join this dot, right? Specifically. And it will be very helpful if you, especially in this section, go back and just revise what you learned from the learning outline. Okay, most of what you've done there will port here in a more general language. There will be some subtleties, and it's those subtleties that we want to explore. If I don't. Sorry. Yeah.
So maybe you request application as well for what is better for the final version.
No, it's reversible as well. So every element of the spectrum is an eigenvalue, every eigenvalue is in spectrum. Okay. So now I'm going to do an example that is a little bit wonky, and it's not continuous by any means, but it's certainly infinite. And I want you to kind of get some appreciation for how things get weird with infinity involved. Okay, so this is called the white shift argument. We'll use it a little later to prove a couple of things, but for now, I just want to define it and tell you how it acts, and then show you that there are some strangenesses involved in the software. So mostly it's just stating what's going on with software, right? So we'll start with the following definition. I'm going to call C infinity the set of sequences A equal to alpha 9, where alpha goes from 1, sorry, where I goes from 1 to infinity, that satisfy the convergence requirement that if I take all of these alphas, which are generally complex numbers, take their modulus squared, add them all up, it's finite. Okay. So satisfying that sum of modulus squared the alpha i's from I equals 1 to infinity. It's fine. This is a convergence requirement on the components of this vector alpha. Okay. This guy is a Hilbert space with inner product defined as follows and basis defined as follows. Hilbert space with inner product between, say, two vectors A alpha A and B. Then inner product between A and B as the sum from J equals 1 to infinity of alpha J plus conjugate beta A is the set of alphas is the components of A, and the set of betas the components of B. Okay. And the standard basis set is this, where this guy denotes a collection of numbers, components of the CI that are zero everywhere except for the ith component. Okay, so EI is the set 0, 0, all the way through to the ith component, which is like a normalized one. Okay. Yeah, question.
Since these are infinite sequences of variable added with trace.
What, which
For EI, there's no variable added to that.
No, yeah, just whatever the ith component, that's, is 782 million. 782 million. Number, the sequence will be one, everything else will be zero. Okay. But you started to hit on the weirdness of this thing, right? So, okay, we've got a basis and we've got a product, so that in this basis, I can write the vector A then as the sum of the j equals 1 to infinity, alpha j, ej. So I can expand this vector in this basis with the components. So now I'm going to define the right shift operator. So what the right shift operator does calls operator R, find the operator R with action on the basis. So R acts on the vector A, which I'm going to expand in this basis set, go j equals 1 to infinity, alpha j, e j. And what it does is it takes this guy and it acts on the j basis vector, take this as sum, take it past the alphas, that's just numbers, and R acts on ej. And what it does is it shifts this guy by 1. Right? So this is sum j equals 1 to infinity, alpha j, e, this is my definition, j plus 1. In other words, if I think of this vector A as a collection of its components, then R maps the collection alpha 1, alpha 2, etc., to the collection 0, alpha 1, alpha 2. So now you see why having an infinite set of vectors is useful. I've taken all the vectors and I've pushed them all by 1, and I need an infinite set in order to say that I can push them all by 1. Okay. But that's what it does. It's a shift operator. It shifts it acts on the basis to shift all the basis all the basis elements by 1. Okay. There are some interesting properties. And one interesting property is that it preserves the normal vectors. So if I calculate the norm of R acting on A, well, this is just A R on A. So R that is R, so that's what it's about. And this is just expanded. On that basis, this is just alpha alpha J conjugate alpha K E J plus one E J plus one. This is of course an orthogonal set, so this is delta J plus one K plus one. And I can sum out over one of those, and you can see that this is just going to be the normal for that area. Right, so R preserves the norm of the vector. This holds for all vectors A. I didn't tell you anything about anything particularly special about vector A, which means that this operator must have a unit norm side by our definition of what the norm of the operator is. Which is okay. And then by the exercise that you guys are going to do, this tells me that for any lambda spectrum of this right-shift operator, the modulus, the absolute value of that lambda must be less than one. Okay. So any lambda in the spectrum of the right-shift operator modulus of lambda is less than or equal to one. So again, what we've shown here is that any element of the spectrum must have modulus less than one. Okay. Now I want to show that the converse is also true, namely that if I find some lambda whose modulus is less than one, then it is in the spectrum. So we show that any lambda C with one lambda less than one is an element of spectrum of on. We need to show that yes, 0 less than or equal to one lambda less than or equal to one, then E plus R minus lambda phi is not invertible. Again, you know, r minus lambda I being not invertible tells me that that I can't invert this. Sorry, r minus lambda I being not invertible tells me that this must be an eigenvalue of the lambda must be an eigenvalue of not strong. Okay, in the finite dimensional case. So it will suffice for us to show that that's the case, even though this is an infinite dimensional setting. It's a countably infinite dimensional setting. It's not continuous, but I mean, density model performance. It will suffice for us to show that the operator is not quantum. So again, this was the statement that I made about the operators in the finite dimensional vector space. They're being invertible, means that they're onto. It'll be enough for us to show that if that is not onto, then it is not invertible. So what does that mean?
I mean, not just because it's countably infinite, if it was.
If it was a continuum, I'm going to replace sums by integrals, then kind of all bets are off, and I'll have to do much more work to do that. Okay. The point here that I'm trying to make is not about, not technically not about it being a continuum or not. It's about infinity, probably in the story, right? So suppose that it is. So we're going to prove by contradiction. Suppose that it's odd. So this means that we must be able to find some vector A in C infinity that maps to, and I'm going to leave this as an exercise for you guys to convince yourself that this is the case, that maps to the first basis vector. R minus lambda identity equals. So of that set of basis vectors, we pick one, E1, and we can find some A, sorry. We can find some vector A such that R minus lambda times the identity acting on A is 1. The first standard vector basis vector of C infinity. So in terms of components, in components, this means that if
Don't you need a weighting on that basis?
what do you mean?
A weighting of A or alpha? Because if it's A, then gives you, you want to make sure that there must be some scale that the coefficient alpha one.
That's exactly what I'm going to tell you. So in components, this necessarily means that alpha one must be minus one over lambda. So it's this way. And that alpha j minus one is equal to lambda times alpha j. And this must be true for all j greater than or equal to 2. So again, I want you to show this explicitly. Just expanding that and equating the coefficients, equating the components. But the point here is that when I do this, when I equate when I equate components, right? What I have is a recursion relation for the alphas with initial condition, this guy here. So I can solve the recursion relation by directly substituting that in, and then I'll get the equivalent of the recursion equivalent of a differential equation, and then I can solve. Right? So we can solve this recursion equation. Yes. That's alpha j is equal to minus 1 over lambda to the j. For all j. But my claim is that this is a contradiction. And that's because the following is true. If I calculate the sum over j of square modulus of all these alpha j's, then that's just the sum j equals 1 infinity of this 1 over 1 lambda to 2j. And remember, our starting assumption was that we wanted to show that the converse of that statement is true. In other words, we want to take mod lambda between 0 and 1 and show that it lives here. So our assumption is that mod lambda is between 0 and 1. So if mod lambda is between 0 and 1, and the square modulus sum of this guy is this, and this is a number between 0 and 1, then this is going to blow up. And we assume that this was a vector in C infinity, which means that all its components satisfy the convergence criteria. So this is a contradiction. Right? Which then means that this is not R2, which then means that R minus lambda identity is not vertical. So what we've shown here is that every element of the spectrum of the sprite shift operator must have modulus less than or equal to 1, and vice versa. Okay, everybody happy? Good. There's one more point that I need to make about this right shift operator before we finish for the day, and that is the following. So suppose I have some complex number that's an eigenvalue of the right component. So suppose that lambda is an eigenvalue of all with eigenvector A. Then I know already that R preserves the length of A. So this means the following. I calculate the square of the length of vector A by taking that inner product that we've already agreed that this is equal to this is the same as calculating in product between the vector that I get from my action with R. But lambda is an eigenvalue of an eigenvector A. This is the same as that. And then I can always take these guys out. It's complex numbers, so that just pulls out 1 lambda squared A inner product A. Which then implies that this must have unit modulus. So now suppose A is the sequence that we have up here. Right, and these numbers could be anything we want, right? But assume that the first, as I go from left to right of the sequence, the first non-zero alpha that I find is in the nth position. Right? So suppose that alpha m is the first non-zero element of what? Then the following is true. If I calculate the inner product between RA and EM basis squared, what do I get? Right, so I've got this vector, right, and I'm assuming that all the components are zero right up until you get to the nth component. And then I act on this vector with the right shift operator. And what does the right shift operator do? It takes that nth component and it moves it to the n plus first space. Right? So now everything before this is zero. So the only non-zero, the first non-zero element I will encounter, I don't care what that comes with. The first non-zero element I will encounter will be the n plus first space. Now I take the dot product, or the inner product, with the mth basis vector, which is going to single out the mth entry. It's going to be 0. Right? But this guy is still an eigenvector of R by assumption, so this is going to be lambda A EM. Right? I can still take this lambda out. Lambda on this conjugate and do that. And then this is going to single out of A, not the right shift coordinate of A, but it's going to single out the mth component, which was the first non-vanishing component. So this is going to be alpha M. In other words, we're assuming we're talking about non-vanishing eigenvalues, which means that this is true if alpha M is 0, but we already assume alpha M is not vanishing. That's not a condition. Good. So I'm going to leave this here, partly because I have no else for that. But also I'll come to the end of this example. It's a weird operation to have, and it's weird to arises from the fact that it's acting in an infinite out of the infinite dimension vector space. Right. We'll return to this for some theorem for it a little later, and the next time on Friday, when I see you guys, we will talk about compact market operators in more detail.